So now we've done all the clicking that we can do here. We're going to have to do some typing. So we're going to go File, New, Data File. And let's call it fluid. So the first thing we're going to do is just sort the fluid situation out. And I'm going to start with restoring the model that we just created. So model, restore. Oh, I called it model, but you might have called it something else. You should note that if you give a restore command, it automatically gives a new command. So you'll see a lot of people, even our own consultants, will say model new, model restore. You don't actually have to do that. When you give a restore, it automatically does a new, then restores. So you don't end up with zones on top of each other, right? Okay, now here's the little magic command that you need when you do densify. You always need this: zone, attach. Oh, no comment here. Zone, attach, by face. And I'm going to leave a comment here for you guys. Use this when densifying. Because remember, there was that disconnect there where some of the zones didn't line up with some of the other zones. So there's, if you don't do this, it'll actually still run, but you'll have these little dangling nodes that aren't connected to anything, and they'll have like big displacements, right? You know, what the heck is that all about? So this essentially attaches those little dangling nodes to the face that they're touching, so you get sensible answers. Okay. Model config fluid. So this just sets up all the zones to be able to take some extra properties like permeability and porosity and so on. If you don't config fluid, I'm sure you talked about this yesterday. If you don't config fluid, you can still have pore pressures. You can put in a water table. You can still have pore pressures. You can still have effective stresses. You just can't calculate fluid flow, right? And in the mining world, a lot of people just do that. You know, they get a water table from somewhere. They put it in there. They get the pore pressures, and they move on with life. In the civil world, people are often interested in calculating the fluid flow. And in this particular example, it turns out to be relatively important. You want to see where the fluid's going in this landfill thing, right? Okay. Zone, fluid. Now, remember when I was talking about constitutive models, we also have constitutive models for fluid, and we also have constitutive models for thermal. There's just not that many of them. So for fluid, you basically have isotropic or not isotropic. So either the permeability is the same in all directions, or the permeability is not the same in all directions. In theory, you could always just say anisotropic and give different. You could theoretically give the same permeability in each direction and get the same answer. But just to save us on typing, we can say zone fluid C model assign isotropic. Now we just have to give one permeability, and it assumes that it's the same in all directions, right? So I can give a permeability here: zone fluid prop perm 1e minus 6. Now, hopefully you talked about this yesterday too, but the permeability in FLAC2D is not the permeability that you think it is. And we've got a plan for the near future to make all these things more intuitive. And I don't know how much Russell talked about it yesterday. But in the short term, be aware that the fluid permeability in FLAC2D is the permeability that you're used to, probably in the world of civil engineering, which is in something like meters per second. You need to take that and divide by the unit weight of water to get the FLAC permeability. So this is actually 1e minus 2 meters per second, right? Because the unit weight of water is roughly 1,000 times gravity, so 10,000. And I don't know if Russell went into it. There are historical reasons why it was set up this way. It was meant to be independent of things like gravity and viscosity. and be as general as possible. So for example, in the oil industry, in the petroleum world, they use a different permeability. They use something in Darcy's, right, which is units of meter squared. And so they have to do some other kind of conversion that involves putting the viscosity in there. So the ITASCA people years and years ago decided that they would try to make something as general as possible, which is this hydraulic conductivity, I guess, that does not have gravity sort of built into it. But most people in civil engineering are used to using what they call permeability, which is, something like meters per second. So anyway, you need to divide by, in the metric world, you need to divide by 10,000 to get the permeability for FLAC. And so that's going to be the permeability for all the soil layers. And for the rock layer, we're going to give it something much less permeable. Zone, fluid, prop, perm, 1E minus 10, range, group, rock. And we also have, we're going to hack it here. We also have a thin, low permeability layer at the bottom of the waste. So with these landfill things, presumably they plop all this landfill on top of some relatively impermeable layer of something. I'm not a landfill guy, but I'm guessing there's some kind of geotextile or layer of something that is relatively impermeable so that all this waste doesn't go down into the groundwater, right? We didn't actually draw a layer in here. I mean, you could theoretically draw a super thin layer in here and actually model it. We didn't do that. So all we're going to do is take a row of zones at the bottom of the waste here and give it a low permeability. And so we're just going to use coordinates. So I'm going to say zone, fluid, prop, perm, 1E minus 10, range, position X, minus 30, that's the left-hand side, to 146, and position Y, minus 3 to minus 1. And so this was actually a little bit of a trial and error to try and pick off a layer of zones that I could give a low permeability to. And again, maybe if I was doing this in real life project for an actual client, I would draw in a layer there and make sure that it worked properly. In this case, we're just sort of hacking it by saying, okay, I'm going to pick a row of zones here, and I'm kind of fudging it by eye to say, yeah, between Y minus 3 and minus 1 is basically where I want to have this low permeability layer. So we can run it. So once you finish typing that in, just run this thing. Console. And let's make a plot. So go here and say new plot. And let's call it, I don't know, zones. So hopefully you've done this 100 times already. You go to the plot item list, take this drop down arrow, and you choose zone. So here's my zones. Again, this mishmash of different group names. Over here where it says slot, same as we did in the model pane, you could choose, instead of any, you could choose construction to see our layers. Make sure we're still good. But what we really want to check here is if we did the fluid properties right. So where it says label, instead of group, change it to fluid property. Where it says hydraulic conductivity, change it to permeability. Look it up. If you just choose permeability as the property. So I've got the rock, which is 1E minus 10. The other stuff, which is 1E minus 6, except for this skinny little layer here at the bottom of the waste, which is 1E minus 10. And you can see here it's not really perfect, right? It picks up 2 zones over here and 1 zone here, but really we just want to have a layer of low permeability material. Couple more properties here. We're just going to set the porosity to be 0.5. Zone, fluid, prop, porous, 0.5. Again, This is probably slightly simplified from the real project in which different layers had different porosities and so on, but just use that for now. And then an important thing here is zone, grid point, any fluid tension, 0. So hopefully you talked about this yesterday, but by default, there's no tension limit, so the fluid never desaturates, right? It allows it to build up negative pore pressures, which maybe is fine. Maybe you've got a material that allows negative pore pressures. Maybe you don't care. Most of the time, you probably have a situation where it hits a certain level of negative pore pressure and it starts to desaturate, right? And so in this case, we're going to say, well, if the pore pressure goes to 0, it's going to start desaturating. But you need to tell it that. You need to tell it that 0 is the cutoff. And if the fluid pore pressure drops to 0, it's going to start, instead of going into negative territory, it's just going to start desaturating. Okay, you also need to set the fluid density. So zone, any fluid dense 1000. Wait a minute. I've done this twice. Let me do an experiment here. Okay, there's this slightly complicated duplication of commands that will be simplified in the near future, but for now, just bear with me. We want to set a water table at the top of the clay layer. We can just say, okay, there's a water table at the top of the clay layer, and it'll work out what all the pore pressures are based on the depth below the water table. But it can't do that unless it knows what gravity is and it knows what the density of the water is, right? So it needs the density of the water and the gravity and the depth below the water table to work out the pore pressures. So what I can say is zone water density 1000, and then model gravity 9.81. And then I can give a water table. Zone water plane. You give the normal. So you could theoretically have a water table that is not horizontal, right? You could have a water table that's on a slant. You could have a water table that's a crazy complicated shape. And you could do that by importing, for example, the DXF, which would just be a 2D line. You can do stuff like that. If you want to just have it planar, you can say zone water plane, and you just give a normal. And the normal is in the direction of increasing pore pressure, so usually down. So 0 minus 1. And then you need to give a location, a point on the plane, right? So I'm going to say origin 0 minus 3. And where that is, let's go back to my plot here. You don't have to do this, but if I go back to my plot and I change it back to group, the top of the clay layer, the top of the sand layer is at minus 3. So this is where I'm going to stick the water table, right? Presumably there was material sitting here with a water table that was basically at the surface, and then they plopped this waste on top of it, right? So I'm going to set this water table to be here at the top of the sand layer, which is basically minus 3. So let's just run it up until now and make sure that I've done this correctly. And you go back to your plot, and you change click on where it's a zone group or whatever. Change the label to contour. Change the zone value to pore pressure. Hopefully it looks like this. So all the waste is 0. And then it increases basically from the top of the sand down to the bottom. Got that? Hopefully. Okay, so we got that in there. Now this is where it gets fun. So everything up until now is probably relatively straightforward. What we're going to do now is assume that there's also water in the top. Okay, but it's almost like there's a second water table there because we've got this water in the top and we've got this low permeability layer that we put in there. And then we've got this water on the bottom that was existing before we ever put the landfill on, right? We don't really know where the water table is at the top. Right? The water table is this is a slope, right? So it's going to be some sort of curving water table here. And we could sort of make a guess at it, but instead we can put the boundary conditions on here to specify where the water table is on the left side. And it's just going to flow and work itself out, right? Which is why we need the flow calculation on. If we were just going to guess at the water table, we wouldn't even need the flow calculation. We wouldn't need permeability. We wouldn't need anything. But what we're going to do here is let it work itself out. So what we need to do is apply the boundary condition to the left side. Zone, face, fly, pore pressure, 19 times 9,810. Gradient, 0 minus 9810. Put 3 dots here, which means I can go to the next line and continue on with my command. You don't have to do this, but I'm doing it so you can see what I'm typing. Range, pause x minus 30, which is the left-hand side. I could have used the group name of the left-hand side. I could have said range group, whatever it was, West 2. But I know it's minus 30, so I'm just going to use that. Pause y, minus 0.2, 19. So let's see if I have a slide about this. Maybe I have a slide that describes what the heck I'm talking about here. Because this is probably the most complicated part of this thing. Properties, phase groups, fluid properties, boundary conditions. Okay. So this is what it looks like, right? We've got this water table here, which we already specified. We just said put the water table here at minus 3. And we've got a second water table here, which is essentially 19 meters of head, if you prefer thinking about things like that. And so the water pressure at this 0 coordinate, well, so where's the 0 coordinate? Let's have a look at our zones again. I'm going to change this back to label group. So the 0 coordinate, so the top of the sand is minus 3. Oh, and then I've got this fun layer of impermeable material. So let's put that back on. Okay, so then I've got this fun layer of impermeable, sort of impermeable material. And so the coordinate here, the y coordinate here, is close enough, is actually 0.2. Let's call it pretty close to 0. So when you give these pore pressure boundary conditions and initial conditions, I could say zone initialized pore pressure, and it would be the same thing. What it does is, I'm sure you talked about this already, you give the value of the pore pressure at the 0, 0 coordinate, okay? And in this particular case, the 0, 0 coordinate is the bottom of the waste, not including this impermeable layer, right? So basically what we want to do is specify the pore pressure at this point. And we're assuming we've got 19 meters of fluid sitting above us here. So if you were using a program that allowed you to put in head, you would just say head 19. Because we're doing pore pressure, it's actually 19 times the unit weight of water, right? So the pressure is just 19 meters of water times the unit weight of water. So I've done a little inline fish here to work that out. And this is actually useful because when I go back to it in the future and say, now what was I doing there? It's like, oh yeah, it's just 19 meters of water. The gradient is the change in pore pressure per unit length in the vertical up direction. And that's always the same. If you're doing stresses, if you're doing pore pressures, whatever, you give the value at 0, 0, and you give a gradient, which is the change per unit length in the up direction. And so the pore pressure is positive down at the bottom, but it's getting more negative as you go up, right? It's becoming less positive. So when you get to the top, it should be 0. If I go 19 meters up, my pore pressure is going to be 0, right? So it goes from 0 to whatever, something else. I'm applying this boundary condition to the left-hand side, so position X is minus 30, but only here, right? Only on top of this layer here. I don't want to apply this boundary condition to the whole left side because it's going to mess up my bottom water table, which I already set up. So I've got this bottom water table, which basically starts here, below this light blue layer, and I've got this top water table, which basically starts here above this light blue layer, and this light blue layer is going to basically be 0 pore pressure. Ish. Some of the top's actually going to bleed into the bottom, but should be close to 0. So this is the trickiest part of this whole thing. Applying this boundary condition to the left side only to the piece of the model that I want to have this pore pressure in it. And then it's going to calculate everything, and you're going to see a water table form in that slope in a sensible way, hopefully. The last thing we want to do is say, we want to make sure that the pore pressure on the surface, we want to make sure that the pore pressure on the surface is 0. So you can imagine if by default, if you don't say anything, the fluid boundaries are impermeable, which means the fluid can't flow through the boundary. And so what would actually happen here, maybe, is that we're holding a constant pore pressure over here. It's going to flow this way. This is impermeable boundary here. So it's essentially going to like fill up like a bathtub, right? Whereas in reality, this is a 0 pore pressure. There's not ponded water in this case. And so by specifying a 0 pore pressure on the surface, it makes sense. You can actually simulate a situation with ponded water. You could specify a pore pressure that's not 0, and it will actually simulate ponded water here. In this case, we're assuming that there's not ponded water. So we want everything that's on the surface to actually have a pore pressure of 0. And we can identify that surface using the group name. Hopefully it worked when we assign the group names automatically. If I go back to my model pane and I click on zone face, this whole top layer here, this pink one is called top, which is lucky. So it makes it easy. So I can just say zone face apply. I can just type P' because I'm lazy. 0 range group top. Okay, last thing we need to do here. So one more tricky thing about this. We applied a pore pressure to the left-hand side above the impermeable layer, and that's fine. That's going to stay. By giving the keyword apply, it's going to fix it, right? It's always at that value. It's just stick there. We said it's going to be 0 on the top. We use the apply keyword. It means it's always going to be 0. No problem. We set up the initial pore pressures below the impermeable layer with the water table. That's the initial pore pressures. They're not necessarily going to stay like that. So when flow is being calculated, those can change, right? But we want to essentially, at least on the left side and the right side, fix those pore pressures, right? Because often into the infinity, that's what the pore table, that's what the water table is, right? So on those boundaries on the left side and the right side, we want to fix that pore pressure that we set already so that they don't change, because we're approximating this infinite water table out to the sides. So we can just give a fix command here. So what you say is zone grid point fix P-P range pause x minus 30, and I could have said pause, or I could have said range group west, or whatever we called it. Oh no, because this is grid points. That would still work. That would still work. And then same on the right-hand side, zone grid point, fix, PP, range, pause y. I know that the right-hand side is at, oh sorry, pause x, 260. Now this is partially redundant on the left-hand side because we already gave that apply condition. It's already fixed. So we kind of don't actually need to do the whole left-hand side. We only need to do the left-hand side below the water table there. So I could say pause y something to something, but it doesn't matter. If I fix it, it doesn't make any difference. So okay, we're almost done here. We can set up some histories because you want to watch the pore pressure change with time. I can say zone is short for history, P-P short for pore pressure, pause short for position. You can see how you get lazy after you've been doing this for a while. You don't type out the whole words, right? Zone his PP pause, and I'm going to put one at 010. I'm going to do the same thing at 95.5. And I'm going to do the same thing at, I can't type. You could just copy and paste, obviously, but 160.0. So let's just run everything we've got so far. Okay, did it work? Errors? If I go back to my plot, I can add to this plot. So if I go to the plus, under miscellaneous, I can choose history locations. And you can see it gives me 3 little cubes here where I'm taking those pore pressure histories. So I can see if I put them in the right spot where I want to monitor the pore pressure. So in theory, at these 3 locations, but at least in these first 2, the pore pressure should start at 0. And then it's going to gradually increase, right? Because we have this boundary condition on the left-hand side, and the water is going to flow this way. And what we should see is pore pressure increasing from 0 up to something and then flattening out, right? And probably for this guy too, probably all 3 of them. And so one of the reasons to take this history is to see if you've actually reached a sort of steady state equilibrium when the pore pressures are not changing anymore, right? Okay, and one property I forgot to set, which is you need to specify the fluid bulk modulus. In this particular case, we're just trying to get to a steady state solution, sort of infinite time. So the fluid bulk modulus doesn't really matter that much. The fluid bulk modulus is important when time is important. In the case where time is not important, we can set it to be almost anything. Hopefully you talked about that yesterday in the fluid class. There is a minimum. You don't want to set it to be some stupidly small number. This doesn't work. So you can kind of work out what that minimum number is, but it's not super important. So what I need to do is say zone grid point any fluid mod. I'm going to use 10,000. So the real modulus of fluid is something like 2 gigapascals, right? So if you were doing a real fluid analysis where time was important, you would possibly put in the real fluid modulus here. In this case, we don't care about time. We can put in a smaller number, and it's just going to converge faster. And so what we're going to do is solve only for the fluid, first of all. So again, we're just trying to get to this steady state of fluid, figure out what the pore pressures are, figure out where the water table is. We don't care about the deformation yet. So you can turn off the mechanical part. So what you can do is you can say model mech off. And then I could say model solve, but it actually won't work because by default, it's looking for a mechanical unbalanced force ratio when I say model solve. I actually just turn the mechanical off. So that's not even going to work. So what I need to do is tell it, oh, actually, I'm now doing a fluid analysis, and I'm going to use the fluid unbalanced ratio instead of the mechanical unbalanced ratio. And it's not a force ratio. It's something to do with, I don't actually 100% know, but it's something to do with the rate of flow into the model versus the rate of flow out of the model, and whether those things are balanced or something like that. So you can say something like model solve fluid ratio flow and give some number. We'd have to look in the documentation to figure out exactly what this means, but essentially, it's some sort of balancing of the fluid flow to tell you that it's reached some sort of convergence. You could, in theory, just give some number of steps, or you can also give some amount of time. You say model solve age something and give some time, and then you can just look at the histories and see when they've flattened out, and you say, okay, now I'm at steady state, right? And then at the end, I'm going to put a save. So before we run this, let's set up a plot of the histories so we can watch them go. So, okay, I'm going to save this file because I just did all that typing, but I'm not going to run it yet. I'm going to go here. I'm going to make a new plot. Actually, we could do two things at once, depending on how big your screen is. You can go here and say split right. Click in that new box and say, give me a new plot. Let's call it histories. And then go to the plus. And under charts, you should see history chart. So double click that. And then hopefully under the attributes, you see the 3 histories that we set up. So you can hit a plus on the 1 and a plus on the 2 and a plus on the 3. And we're going to see 3 different curves here evolving, hopefully, as this goes. So now I can click back in the left-hand side and just hit the green button. And it's going to run the whole thing, hopefully. Something went screwy there. Hold on. Oh, no, here it goes. So yeah, history point number 1 starts feeling the pore pressure first. And then hopefully at some point, we're going to see number 2 start to pick up. While this is going, you can go here and change the plot. See where it's the drop down where it says histories. You can change it back to the zones plot. And I could change it to contour pore pressure. So I could watch the pore pressures evolve in this plot here. Or I can watch the pore pressures evolve in my history plot, whichever you prefer. All right, here comes number 2 now. You can see my little wheel flashing here. I think by default, it updates the plot every 100 steps. You know, this is doing thousands and thousands of steps, so we don't need to necessarily update every 100 steps. I think if you check this little view settings box here, oh, that's not where it is. You don't have to do this, but if you go to edit, no, sorry, tools, options, plots, under here, it says update interval 100. I can change that to 1,000. So I'm going to update the plot every 1,000 steps and go a little bit faster. Let's go back to my other plot, see how it's doing. So hopefully yours is looking something like this. You can see how there's this water table at the bottom. There's this layer of low pore pressure, and then there's this water table forming at the top here. This kind of depends on how fast your computer is, and I don't know if Russell talked about it yesterday, but he's almost finished with an implicit solution for this thing that goes way faster. So you basically get to the steady state in like 2 seconds. So that should be in an upcoming update at some point. But for now, it's using this explicit. Okay, mine's done. Took 3 minutes. So you can see how these are leveling off. If you wanted to be more accurate than this, you could give a smaller number here for this ratio flow, or you could just execute more steps by hand. Just say model cycle, another 50,000 or something. We're going to assume this is good enough. Actually, I'm not even sure what the default is here. Let's just see if it tells me. Model solve. Doesn't even tell me what the default is. Model solve fluid. Yeah, cycles total. Ratio flow. Yeah, I don't know what the default is. I have to find it. Maybe there's no default. Look at your zones. If you're on a laptop, this screen is probably a bit small, so you could just close this right-hand side. And in the left-hand side, you can just choose your zone plot from the drop-down. Get a nicer view here. Hopefully it looks something like that. We're forcing the pore pressure to be 0 to, or the head to be 0 to 19 on the left-hand side here, above that layer. What I was going to say is if you ran it forever, then it would bleed through this layer and everything would equilibrate, but that's not actually true because of the fact that we're forcing this boundary condition on the left-hand side. Fluid stuff is a little bit complicated, and I'm sure Dave talked about it yesterday, but he's worked on simplifying all this and making life easier. So in some not too distant future, doing this kind of analysis is actually going to be quite a bit easier. It's not harmful to necessarily understand the concepts of what's happening here behind the scenes, setting all these properties and doing things. In the near future, you're going to be something like, okay, solve to steady state, and it's going to solve to steady state. It's going to automatically turn off the mechanical and turn on the fluid and do some of these other things that we had to type in by hand here. But anyway, hopefully you know how to do it.